So, Ireland, you asked me a question. Let's see if I still have it on my screen here. You said about positive and negative real zeros and imaginary zeros. And you understand you count the times the signs change. Okay. And this is kind of a big topic that, it could be that we got to go back further than this, but I'm going to go ahead and do what I can, specifically related to that topic. And if I see it tomorrow and you need something more, you could tell me. So the first thing that you need to understand is that when you have a polynomial function like this in example of 4, that the number of complex zeros is always equal to the highest power of x. So in this case, the highest power of x is 6. So the total number of zeros, meaning the values that you would plug in for x and make f of x equal 0, is 6. You can see that in all 4 of those lines. They're going to say the total zeros is 6, because that you can tell directly by looking at it. Now we know that a certain number of those zeros will be real numbers, and a certain number of those zeros can be imaginary, because these zeros here are called complex numbers, and complex numbers are made up of real numbers and imaginary numbers. So we know, in any case, it's going to add up to 6. What we're being asked right now is, how many real are there, how many imaginary, and how many of the real numbers are positive numbers, and how many of the real zeros are negative numbers. So this Descartes' rule of signs says that if you count the number of changes in sign in the polynomial function, that would be the most number of positive zeros that you would get. And if it's not that number, it has to be less than that number by an even number. So for example here, let's look at the first term is a positive term, the second term is a negative. That's a change of sign. Right now we go from the second term to the third term, goes from negative to plus. That's another change of sign. Then it goes from positive to negative, and the rest are negative. So how many total changes of sign was that? 1, 2, 3. Okay, so the most positive zeros there could be is 3. And that's why in this column here, they're saying 3 and 3. Now, how many negative zeros could there be? In order to get that, you have to substitute for the x here, and here, and here, and here, and here, everywhere. Put in a negative x and see what that does. I mean, here's where they put in negative x for x. And every time you raise negative x to an even power, you get a positive term, which means it didn't change. Every time you raise the negative x to an odd power, it's going to change the sign of that term, right? If I have negative 1 to the first power, that's negative 1. Negative 1 squared is positive. Negative 1 to the third is negative again. So you got to look for all these terms that have odd powers. When you plug in the negative x, they change their sign. So you don't really have to go through this step right here. You're just going to take this function, and all of the odd power terms, change their sign. So that's what this line is right there. That the 2x to the fifth is now positive. The 10x to the third is now positive. And the 8x is now positive. So this changed the sign of those terms only. Okay, now count the changes in the signs of the terms. So it's positive, 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 negative, positive, negative. So how many changes of sign was that? That was 1, 2, 3. So the most negative real zeros is 3. All right? But it could be less than that by an even number. So it could be 3 or it could be 1. So these two columns here are telling you, okay, you could have 3 real zeros, or you could have 3 positive zeros, and you could have 3 negative zeros. That would be okay because they would add up to 6, and you're allowed to have 6 total zeros. But it's possible that you could have 3 positive and 1 negative. It could be less than the 3 by an even number. Okay, but if that's true, then you're going to have 3 and 1. There must be 2 imaginary because they all have to add up to 6. Right? Now, all we're really doing here in these two columns is taking all the possible combinations of 3 or 1 positive zeros, 3 or 1 negative. So it could be 3 and 3, 3 and 1, 1 and 3, 1 and 1. And then what's left here is the number of imaginary zeros, but making sure that in every one of these rows, it's got to add up to 6. Okay, so that's the idea behind this. Now, if we go to some examples here, if I was going to make the same table that we just saw in that example, then I know that it would look something like this. I'm going to make and sorry, my writing is bad here because I'm writing on a really slippery screen. And I know I need 4 columns. I really don't know how many rows that I've got. But this is going to be our positive real zeros. This is going to be our negative real zeros. This is going to be our imaginary, which means I. And the total are complex C. So let's see, how many changes of sign do you see here? Positive, positive, negative. 1. Okay, so you're either going to have 1 positive real zero, or you could have less than that by an even number. But that doesn't make sense because 1 minus 2 is negative 1, and you're not going to have negative 1 zeros. Okay, now if I find f of negative x, that's going to change the odd power term. So this x to the third is going to become negative x to the third. And this 2x to the first will become negative 2x. And this minus 11 doesn't change. Okay, how many changes of sign do you see there? And the answer is none. So there's not going to be any negative real zeros. So really the only possibility here is you got 1 positive, no negative. There's a total of 3 because it's a third degree polynomial, which means how many imaginary? 2. Okay, this one ought to be a little more interesting. Here's my positive column, here's my negative column, here's my imaginary column, and here's the total number of complex zeros. How many changes of sign? 1, 2, 3, 4. So we could have 4 or 2 or 0. I'm going to do it like this since we're counting it 4, 2, 0. We may have to repeat that in a minute, but okay, now if I do g of negative x, that is not going to change the sign of the first term, so it's 2x to the fourth. It is going to change the sign of the second term because that's to the third power plus 8x to the third. It's not going to change the sign of 6x squared, so that's plus 6x squared. It is going to change the sign of the 3x. And then, of course, the 1 doesn't change. So when we do the g of negative x, we actually get a polynomial which has no sign changes. So we know there's no negative real zeros. Now, since this is a 4th degree polynomial, we can say for sure that the total number of zeros, the complex zeros, are 4. So now we can fill in for the number of imaginary zeros. 4 plus 0 plus 2, plus 0 equals 4. 2 plus 0 plus 2 is 4. And 0 plus 0 plus 4 is 4. So those are all the possible combinations of positive and negative real zeros and imaginary zeros. Now you should know already that these numbers here always are even numbers. Imaginary zeros always occur in pairs. Hopefully that's not new, but if it is, now you know. Okay. Now I'm going to show one more example, which is only somewhat related to this, but it followed right after, and I thought I'd show it to you. I mean, I can tell you that when kids are learning this in school, most of them are using a graphing calculator for some of it. Not really what was on the last slide, but what's on this slide right here. Understand that when it comes to zeros, first of all, the number of complex zeros is always this number right here, 6. Right? Now, the number of real zeros, and I'm not talking positive or negative, I'm just saying the total number of real zeros can usually be approximated by looking at the graph, because real zeros are where the graph crosses the x-axis. So, looking at that there, it would appear that there's 2 real zeros. Now, how many imaginary zeros would there be? There would be 4, right? Because if there's 2 real and a total of 6, then there would have to be 4. Now, what was I going to say? I mean, if we wanted to do the positive and how many positive and how many negative, I could look at this here and say, let's see, there would be 1 change of sign, 2 changes of sign, 3, and 3. So the number of positive could be 3 or it could be 1, right? 3 changes of sign, you have to consider it could be less an even number, right? If I did this with if I did f of negative x, it would change this to a positive because that has an exponent of 5. It would change that to a positive because the exponent of 3. And it would change that to a positive. Is that the one we looked at before? Let me go back to the textbook. I have a feeling that's actually the one we already looked at, isn't it? 6x squared minus 8x. Yeah, that's actually the same one. So we're actually repeating an exercise that we already did. But again, you can look at this now and say there would have been 1, 2, 3 changes of sign. So the table is the same one as they had in the book before. So it would appear that there's the 1 negative and there's 1 positive, and that's it. Now it's actually a little more complicated than that. Because usually if you see something like this, if the zero, if the graph looks like it's going through the x-axis at that 0, again, it doesn't really mean that it's there once. That could be what it looks like when there's 3 zeros, as long as it's going through the graph. Right? If it's there an even number of times, it looks like that. It bounces off the graph. But these are all concepts that you should have gotten to already if you're asking a question that comes from this section now. So anyways, you could tell me if I see you tomorrow, Sunday, if you see this today, if you think that there's anything more that I need to help you with on this. Okay? All right.